on this problem, it's a beam that is fixed to a wall with a distributed load of 8 kilonewtons per meter right here, and then a load, or a force at the end of 6 kilonewtons. So first I draw the free body diagram. There's a moment at A because it's fixed. I draw AX and AY because I detach it from the wall. I found this point load right here of 12 at 0.75, and then there's a load of 6 kilonewtons at the end of the beam. Sum up the forces in the x direction because we're going to find our reactions. So we add up the forces in x direction. AX equals 0. In the y direction, AY minus 12 minus 6 equals 0, so we find AY equals 18 kilonewtons. And then the moment at A, since we have the moment here, it's the moment at A minus this force times 0.75 and minus this force times 3. We find the moment at A is 27 kilonewtons times meters. So for the diagrams, I just set this up directly under the picture. So first, AY equals 18, so we start to jump up at 18, and then there's a linear decrease of for the duration of this point load, and it ends at this point load of 12, or it's going to decrease by 12. So by the time we get to the end of the point load, we will have decreased 12, which will bring us to 6. And it continues, there's nothing there until the very end. We get to the end, and with this force of 6 will bring us to 0, which is what we expect. On the moment diagram, it is the integral of the shear, and so we see, since this is positive and since it's going from large difference to, or a large slope to a smaller slope or decrease, it's going to go in this direction up, and it's also going to be going here. There's a moment at A, that's why we start at negative 27, and then once we get to the end of this distributed load, we'll be at negative 18, and then from there we decrease to 0. And we found that by finding the area of these surfaces.